Hello everyone, this is the course corrosion failures and analysis, and lecture 2. And in the first lecture we could complete the first topic. The second topic is forms of corrosion. So, we will take this particular topic, forms of corrosion. Right. Now, as we see in the last lecture that there is a relation between corrosion and materials tetrahedron. Fine, and this is related. We have taken examples like 18-8 stainless steel, and we should see that there is a strong relation between corrosion and material tetrahedron. It is not only that, we have also mentioned that there is also interplay of environment on corrosion, as well as environment also has interplay with materials tetrahedron. For example, I am just one example I can give you here. Let us say you have taken a 0.8 weight% carbon steel, okay, which is paralytic in nature, paralytic, 100% paralytic. Now, if you heat this particular steel in air, okay, where we have oxygen, you would see that if we consider a steel, cylindrical steel, let us say this is a small disc you have cut through. So, that means, so you have taken a small disc and this is that disc, okay. And if you do the microstructure after heating this particular 0.8% carbon steel at around, let us say 600 degrees Celsius for a long duration, you will see after you etch that particular microstructure around that particular periphery, you will get a white layer. So, that white layer is nothing but decarburized layer. Decarburized layer. Why? Because the carbon reacts with oxygen, it forms CO2 or CO. You can balance. Okay. So, these two reactions can happen, and when these two, of course, there will be reactions between iron, FeO, then Fe plus O2 equal to Fe2O3, where I can 3 by 3, here I can put 4 and here I can put 2. So, these are balanced. Those reactions also can happen. So, those will be like rust that is forming on the top layer, which is oxide layer. But the major observation would be, if you see the microstructure, you will see that the white layer has formed. The internal section will see perlite, okay, but outer section there will be a white decarburized layer. This is the typical problem. In case of cast iron, for example, grey cast iron, there the carbon content is of the order about 3 weight%. So, there also we could see that kind of decarburized layer, which looks like a white section. Why white section? Because when you etch, the higher the carbon, higher would be the etching tendency. It would get grayish in color. So, now if you take 0.8% carbon, so there we have, if we see the microstructure, these are pearlite, and these are pre-austenitic and grains. Now, if we etch it, if we let us say 3% nitrile solution, which is the common etchant for carbon steel, and if you hold it long duration in that particular steel, if you do immersion etching, there is a possibility that the surface might get burnt. You would see some strange color appearing on the surface. So, those are actually burnt surface, and that means you have to hold it for a lesser duration. But if you take 0.1% carbon steel, let us say here you have held it for 5 seconds and here you have held it for 5 seconds, fine, both are 5 seconds, but in this case the burning tendency of the surface by the nitrile would be much higher compared to this section. So, in fact, if you hold it for 5 seconds in case of 0.1% carbon, you will not be able to see the microstructure under the optical microscope, because it will not get aged properly. So, that means it is always advised that 0.1% carbon you always use, mostly use nitrile 5% nitrile solution. So, there the etching would be much better. Now, why this difference in reactivity coming? Because of the higher carbon. Now, here also, since you have dipped it in the same solution, and this is the carburized layer, because here the carbon content has gone down, let us say 0.8%, it might go down to 0.1%. So, that means it is obvious that the pearlite content, as you have seen last lecture, that if we have a 0.1% carbon steel, it is mostly ferritic and pearlitic would be along the grain boundary only. So, that time it will look like a whitish in nature, because the pearlite, since there are ferrite and cementite, it looks a greyish color rather than ferrite. The ferrite would look like a very bright color under the optical microscope. So, that is what it looks like, a white layer. Same happens with graphite, because there we have, in case of grey castoreum, where the microstructure is either in case of grey castoreum, either it will have graphite flecks in a pearlite, or there could be possibility of graphite flecks in ferrite pearlitic microstructure. So, again, wherever the graphite flakes are there, after etching it will look like a grey color, and if there the carbon content is less, the graphite formation would be less and the ferrite formation would be more, then the surface would look like a white color. So, this is basically a kind of effect, one small effect I have just narrated, that environment can have a huge effect on materials tetrahedron, that composition can change, microstructure can change, and of course, if these two things change, there will be a possibility of change in properties. Okay. Now, there is one more example. Instead of O2, you can have let us say a carbon environment. Let us say in a graphite, for example, this particular thing, this slice, you put it in a carbon environment, okay, let us say coal or charcoal, you can put it, you will see that this segment that time would be much darker in color compared to the inside part. And one example is, if you see the normal blacksmith, the usual blacksmith who makes those axes and all those things, you will see that they, after making that particular iron object, they push it in the coal environment. Okay. So, that actually helps to do form carburized layer. So, that means the carbon content in that particular layer would go up, and that would give you extra strength or extra wear resistance of that surface, because higher the carbon content, higher would be the hardness. This is a kind of thumb rule. Okay. So, this is the effect of environment on materials tetrahedron, but if I consider the effect of environment on corrosion, it is also extremely critical. Why I am saying environment effect? For example, if you take 0.1% carbon steel rod, you keep it in Ladakh, and another one which is in winter the temperature goes sub-zero, minus 10 degrees Celsius or minus 5 degree, depending on that day winter periods, Some places it might also go to 20 degrees, minus 20 degrees Celsius. Now, another the same processing, you take it to Kanpur, where the winter temperature around 3 to 4 degrees Celsius. Now, the same one you take it to Bombay, winter or maybe Chennai. So, these are different cities in India. Okay. So, Chennai winter temperature could be around 29 degrees Celsius. In addition to that, in Ladakh, if we consider the chlorine percentage, the chloride content would be minimal, and in Kanpur the chloride content, there would be chloride content in the environment, and Chennai, of course, you will see a lot of chloride content. Why? Because it is basically a sea facing city. Okay. So, there you have the chloride ion presence, huge amount of chloride ion presence, and the temperature is also high. And if you see the corrosion of this particular steel in 3 different cities, you would see that here the corrosion would be less. Kanpur the corrosion would go up, little up, but in Chennai the corrosion would be maximum, because it is not only temperature, at the same time there is the presence of chlorine. And another thing we have to consider, that moisture content, H2O. Moisture content in Ladakh would be minimal, because it is a very dry city, very dry city, it rains very little. But Kanpur, it is not that dry compared to Ladakh. So, there will be moisture presence in the environment, but Chennai, it is full of moisture. So, that means these 2 factors, those are the 2 huge culprits which induce corrosion. Okay. So, these 2 factors, those are actually, you can say, demons if we consider the corrosion of metals and alloys. So, these 2 demons would try to damage the steel to a great extent. Fine. So, that means you could see that the environment plays a huge role in inducing corrosion. Okay. Now, so that means here I have less chlorine, almost negligible chloride content, but at the same time dry. There will be presence of chloride content, chloride as well as moisture, but not that moist. In the winter, Kanpur becomes very dry. So, this is dry, little dry I would say, little moist I would say. Sometimes in Kanpur in winter it rains, so that means the moisture content goes up. But Chennai is wet environment, it is very patchy, because in the winter also people sweat over there. Okay, wet as well as chloride content. So, these 2 factors would induce corrosion to a great extent into that particular 0.1% carbon steel. So, that means environment has effect on corrosion. Now, this materials tetrahedron has effect on, has a relation with corrosion, environment has relation with corrosion. Now, that means we must find a kind of synergy between materials tetrahedron and environment to understand corrosion, and if we understand corrosion, we can definitely check for corrosion routes, the protection routes which can minimize corrosion. So, that is the sole purpose I have brought in materials tetrahedron factor, and you will see the influence of that material tetrahedron as we go ahead when we talk about protection process. Now, coming to the different forms, if we have environment, if we have corrosion in that metals, that corrosion might look different, okay? And in fact it looks different. For example, if we check my introduction video, which is almost about around 6 to 7 minutes video, I have shown you different corrosion in the day to day observations. For example, one corrosion, if you go there, you can see that in Kanpur, that one particular house roof, the railings are made of iron pipes, and those pipes have got heavily corroded. The portion which is inside the concrete, that inside the concrete it is so much corroded that the concrete has actually broken apart. So, there one form of corrosion, and you would see one clock I have shown you, if you recall, that clock there also around that key portion the corrosion is more prevalent rather than other parts of the clock. Okay, so, even for example, if you see rebar on the road, just go by and if you see the rebar on the road, you just take a small piece of rebar, you will see that the rebar, if we just take an example of rebar, these are basically ribbed rebar, and you will see, you just closely observe this segment, this section, the rib portion and the foot of that rib portion, you will see that the rust, the red rust is prevalent over there rather than the entire section of the rebar. So, this portion you would say, you would see very little rust which is red color, but if you see the root of that particular rebar, you will see the rust is forming predominantly over there. So, here around those segments the rust is less, but here the rust is more. But if you take a plain bar, without rib, you will see the rust is more or less uniform over the entire segments, more or less uniform. So, that means all the places you will see rust, but here the rust is here and here rust is uniform, but here rust is localized. It is very clear, if it is a plain bar and if it is a ribbed bar, the rust position changes. So, that means the form is different. So, this is more or less crevice pattern, we will learn later, and this is uniform. Now, let us say I give an example, like let us say a rivet. Rivet. So, this is a rivet, two plates are joined together. You will see that this portion where crevice is forming, there the corrosion tendency would be more rather than the other parts. Now, let us say you have a copper plate and steel plate or carbon steel, they are joined together, okay, or let us say they are closely met and tighten it and leave it to NaCl solution, you will see that this portion will be highly corroded, the portion which is in contact with copper. Here also the form is actually changing, the corrosion form or the corrosion pattern is changing. Now, on the basis of this corrosion pattern, we can define different corrosion, okay. And as you see the corrosion pattern is arriving, as we go ahead we will see that there are different factors which lead to such corrosion patterns, okay. So, let us check what are the corrosion patterns. Let us check corrosion patterns and let us see different factors. Okay. Now, one part is the first corrosion pattern you would see, for example, here the plain rebar where the corrosion is more or less uniform over the red rust forms over the entire surface of the rod. So, when the corrosion happens uniformly over the entire section, we call it uniform corrosion. So, now if you see a 3D picture, you will see the corrosion will be if you say the top part is exposed to the electrolyte, you would see the corrosion is uniformly happening through the body section, through the depth direction. If the distance here is 5 millimeter, here it would be 4.92 or 4.95 millimeter. So, almost same sort of depth attack. Okay. So, those are, we can call it uniform corrosion. So, then the second one we have, say, galvanic effect. And here if you see, the galvanic means we also call it two metal corrosion. Fine. So, in the case of two metal corrosion, if one metal is joined to another metal, and if these both metals have got difference in their activity in that particular electrolyte, we have difference in corrosion of those two metals. For example, this is a classic example, copper and steel. So, if let us say steel, let us say these two steel plates are fastened with a copper bolt, okay. This is copper and this is steel. You will see that this portion, if they are under electrochemical attack, this portion will get more corrosion, and mainly the steel corrodes, not the copper, because, and this is let us say NaCl solution or seawater solution. So, because in seawater copper act as a noble component and steel act as an active component. Fine. So, that is what copper does not corrode much. It does not mean that the copper will not corrode, copper would also corrode, but if we see the corrosion rate of both the steel and copper, steel corrosion rate would be much higher than the copper corrosion rate. Fine. So, this is called two metal corrosion, and remember this is very important. In some of the cases there is a kind of misconception that a galvanic effect, if we have two metals, one metal does not corrode, another metal corrodes. It is not true, both metals corrode, but the corrosion rate of one active metal will be much higher than the other metal. Okay. Please remember, two metal corrosion does not mean the corrosion rate of both the metals would be, so one metal would be 0, another metal is maximum, or the it is taking place. It is not that, corrosion happens in both the cases. Fine. Now, third is basically we have another corrosion pattern which is called de-alloying. So, de-alloying, I have mentioned this de-alloying just after galvanic effect. It is basically the preferential corrosion of one element in an alloy. For example, copper zinc. Copper zinc, let us say this is 70-30 copper, and if you expose this one to even potable water, zinc, if we see a 3D picture, so let us say this surface is exposed to the potable solution. So, around this part zinc would mostly zinc would go into the solution and it will leave copper behind. So, this particular segment will look a very red like compared to the orange color what we see in case of normal brass color. Okay. Here it will be very red like, because the copper content goes up to around 90%, even 95%, and the zinc content decreases to 10 to 5% from 30% zinc. So, that means zinc is preferentially going into the solution and copper stays back. This is dealloying. So, we will have other examples also in case of dealloying. Now, fourth, we have crevice. Crevice, for example, here, wherever there is a crevice or sharp corner, that portion can experience this kind of crevice corrosion, which is very, I would say, deteriorating, or I would term this word called deadly corrosion. This is a very bad type of corrosion. Then fifth, we have pitting. This is also extremely bad corrosion, deadly. And if we see a 3D picture, on the flat surface you might see the small black dots, and if we see the under cross section, that particular segment can go deep into the material, deep into the material. What exactly happens there? Actually, if this is the load carrying body, the actual load is carried by the smallest cross section. So, you are not able to see how far that pit has moved in, but you would see that suddenly the material breaks down. Okay. So, this is what happens in case of pitting. Pitting can happen on the flat surface also. Okay. Even if it is a microscopically smooth surface also, pit can happen. So, that pitting is also extremely important corrosion form. Then sixth, we have intergranular corrosion. In case of intergranular corrosion, if we see a microstructure, these are the grains and this is the grain body. So, this is grain body, this is grain. Corrosion happens along the grains. So, that is what it is called, intergranular corrosion. This happens in case of sensitized stainless steel. Fine. Now, seventh is erosion corrosion. Wherever there is a erosion factor which is a mechanical in nature, in addition to that we have electrochemical components. For example, if we see an example of pipe corrosion, let us say this is a pipe and emulsion is going through. That emulsion will have the strongest effect around this zone, and this portion can leak, and there will be a possibility that emulsion will leak out. So, this example, this is a particular example where it gives you mechanical erosion, at the same time corrosion factor is coming into picture. That is what it is called, erosion corrosion, and it has two variants. One is fretting, another one is cavitation. We will talk detail about these two particular forms of erosion corrosion. And finally, we have stress corrosion. Stress corrosion. And in case of stress corrosion, as the name suggests, corrosion plus stress. When these two things combine, we can have catastrophe. The entire bridge can fall down because of the stress corrosion. Okay. Entire component of a particular holding structure can break down because of stress corrosion, and the stress corrosion has to be looked at very carefully, because many of the catastrophic corrosion failures happen due to stress corrosion. So, I would request you to go to a site called Corrosion Doctors. There is a section called failures of components, industrial failures. So, that portion I would request you to look through, or otherwise I will bring it in and then show it to you in the next class. Okay. And the stress corrosion, there are two sections. One is, there are two other variants. One is corrosion fatigue, another one is hydrogen embrittlement. So, this stress corrosion, if we consider the normal stress corrosion, you should make sure that the stress which is there, which is mainly tensile stress, that stress is below the yield stress of that material. So, that time we call it stress corrosion. Now, if it is a corrosion fatigue, then definitely as you see the fatigue term coming into picture, there is an alternate stress variation and corrosion is also party to it. So, this kind of corrosion happens when there is a rotating object. So, now if we come to stress corrosion, whenever we talk about stress corrosion, normal stress corrosion, where the stress is tensile in nature, tensile, and it should be below yield stress of the material. So, that time we call it stress corrosion. Now, corrosion fatigue, as the name suggests, that fatigue load is coming in and also there is a corrosion effect. Fine. Now, fatigue load means there is a variation in load. One time the load goes down, one time load goes up. It could be all tensile and there could be compression tension kind of thing. So, the fatigue itself is a very deteriorating effect to the material failure, okay. But if you have corrosion also, then it actually gets enhanced to a great extent. That means it fails much quicker than a normal fatigue. So, this is one factor, corrosion fatigue. And hydrogen embrittlement, if you consider, this is also very important in the sense that wherever there is a chance of atomic hydrogen H, and that can form from this reaction. This reaction, this hydrogen forms, and hydrogen gets into this material, diffuses, and when it diffuses, it reduces the cohesive force, okay, between the atoms. So, that means it actually reduces the load carrying activity. So, that is what it is called embrittlement, and this hydrogen can induce embrittlement in different ways. One is it reduces the cohesive force between the atoms of that particular metal, or it can react with some of the elements of the metal. For example, zirconium, if there is a zirconium hydride can form. So, those hydrides are very brittle in nature, and those brittle hydrides can break when there is a load effect. So, this particular hydrogen embrittlement, for example, pipeline steel X80, X70, those are line pipe variants of steel. So, their hydrogen embrittlement should be studied very carefully, because those steels are used for pipeline making, and those pipelines migrates or the takes oil from one country to another, the cross country pipelines. So, those pipelines, if there is a hydrogen embrittlement effect, you never know the oil is leaking somewhere in between, and before you could tap it, by the time there is a lot of oil loss. So, that is what you have to test its hydrogen embrittlement behavior in order to prevent oil leakage, because that hydrogen embrittlement can lead to failure of that particular pipeline or the breaking of the particular pipeline, and once that pipeline breaks, oil spills out. Okay. So, that is what you have to be very careful in that stress corrosion part. We have to concentrate on that, how it happens. So, those things will be discussed in greater details. Now, coming to the factors, different factors, and different factors, if I have to name those factors, I just name those factors, discussion will happen in the next lecture. So, for example, environment. Environment, it could be dry, it could be wet, it could be dry, wet, it could be SO2, CO2, SO3, acids, chlorine ion, bromine ion or halides. There would be possibility of deleterious metallic ions, for example, copper plus plus. copper plus plus, if it stays with the potable water and if you are carrying that potable water through a metallic steel pipeline, there is a possibility of leakage. We will discuss why that leakage happens. Okay. So, those are the different environments you can come across. Then there is a possibility of metals composition, microstructure. Okay. Then processing. So, this processing changes microstructures. Then there will be possibility of design. Faulty design is, even if the corrosion effect is there, if it is a faulty design, that magnitude of corrosion failure would be extremely high. Okay. It can be multiplied if there is a design failure. Okay. So, we will talk about that. Fine. So, then whenever we are talking about design, we are talking about how those metallic combinations are chosen. Metallic combination is chosen. So, it is impossible to develop a structure with the same metal. If it is a big structure, you have to use different metals. So, but the combination is very important. So, that comes under design. So, we will talk about that also. So, roughly these are the different factors. We will talk around this. So, let us stop here. We will continue our discussion on corrosion failures and analysis in our subsequent lectures. Thank you.